This is a model 4 second video, that is a video number 4.1, and in this video I will be discussing the garage door opener example for designing the architecture. In the previous video I have been discussing that is what are the input required to design a garage door opener software. The inputs are mainly functional requirement as use cases, constraints, quality requirements expressed as a system specific quality scenario. These are the inputs required to design a software called garage door opener, and a scenario for garage door opener, and that is what are the conditions or situations will be faced while using this kind of system. That is device and controls for opening and closing the door are different for various products in the product line. Means the door size will be different, the door direction will be different, the type of input it takes, that is the type of input operation, that is with the switch it may operate, with the remote control it may operate, or with the home information system it may operate. So the opening and closing the door are different for various products in a product line. The processor used in a different products will be differ. For some kind of products we require that is some of a specific speed of processors. For some product we require a high speed processors, and so, for some products we require a minimal speed processors. So if an obstacle is person or object is detected by the garage door during descent, it must stop within a 0.0 second. Okay, when with the software we are operating the door, if an obstacle, the obstacle may be a person or an object, is detected by the garage door during the descent, during the operation, it must stop within a 0.1 second. The garage door opener system needs to be accessible from the home information system for diagnosis and administration. That is the opener system needs to be accessible from home information system for the purpose of diagnosis and for administration. And it should be possible to directly produce an architecture that reflects this protocol. That is this is different scenarios we may face while operating this software. And ADD steps are like this. Step involved in a attribute driven design, that is choose the model to decompose, because this ADD works on the concept of decomposition. It takes a different customer feedbacks, and the customer is satisfied, then it will release the final version. If the customers are not satisfied, then the iteration may takes the forward backward step, and again decomposition start, that is choose the model to decompose. This is the first step. Start with the entire system. Inputs for this model needs to be available all the time, and constraints, functional and quality requirements must be available. And the second step is refine the model. In the refining the step, what happens, we need to choose architectural drivers relevant to this decomposition, and choose the architectural pattern that satisfy these drivers. Many patterns were available. Depending on the specification, we need to choose the drivers in order to satisfy this architecture. And third step is instantiate modules and allocate a functionality from use cases representing using multiple views. And fourth step is define interfaces of child model. And fifth step is verify and refine use cases and quality scenarios. Repeat for every model that needs further decomposition. Next step is Discussion of the above step in more detail are given. That is, choose the model to decompose. The following are the models: system, subsystem, submodel. This is a main system. Depending on their quality, behavior, we can divide the system into subsystems here. And next one is again subsystem can be divided into submodel in order to make ease of work. And next step is decomposition. Typically start with the system, which then decompose into subsystem and then into submodels. In our example, the garage door opener is a system. Opener must interoperate with the home information system. Refine the model. Choose the architectural drivers. Refining the models. So the first step is selection of architectural drivers, and another step is selection of architectural patterns. These are the two important steps while choosing the architectural and models. That is, choose the architectural drivers from a quality scenario and functional requirements. What should be the quality and what are the functional requirements? Considering these two factors, we need to select architectural drivers. The drivers will be among the top priority requirements for the model, as we discussed earlier. In the garage system, the 4 scenarios were architectural drivers. By examining them, we see real-time performance requirement and modifiability requirement to support a product line. And requirements are not treated as equals. Less important requirements are satisfied within a constraints obtained by satisfying more important requirements. This is a difference of add from the architectural design methods. And second important factor is for each quality requirement there are identifiable tactics and then identifiable patterns that implement these tactics. The goal of this step is to establish an overall architectural pattern for the model, and the pattern needs to satisfy the architectural pattern for the model tactics selected to satisfy the drivers. Two factors involved in selecting the tactics, that is architectural drivers themselves. Means when you choose any pattern, it should not produce any side effects. Sorry, if it produces side effects, then side effects of pattern implementing the tactics on other requirements. While choosing a pattern, while designing the architecture, sometimes we choose the wrong pattern. In that case, we'll get a different kind of side effects. Again, we need to implement a tactics such a way that to get rid of these side effects. This is the following tactics: semantic coherence and information hiding, separate responsibility dealing with the user interface, communication, and sensor into their own models. These are the tactics we can apply in order to get rid of the side effects, that is a semantic coherence and information hiding. And increase the computational efficiency. The performance critical computations should be made as efficient as possible, and it must be scheduled wisely. The performance critical computation should be scheduled to ensure the achievement of the timing deadline, that is user interface, no performance critical computation, performance critical computation, virtual machine, and scheduler that guarantees deadline. This is a UML design. It starts with a virtual machine, okay, simultaneously scheduler that guarantees a deadline, and these two cases work simultaneously for the case called non-performance critical component. Here performance critical composition and virtual composition act simultaneously in order to provide a appropriate user interface. And this figure we can name it as a architectural pattern that utilizes the tactics to achieve garage door drivers. And third step is instantiate modules and allocate a functionality using a multiple use. That is, instantiate modules, allocate a functionality, and using a multiple use. How to instantiate modules means how to start the modules, how to start the performance. The non-performance critical module becomes instantiated as a diagnosis and lowering a door modules. We also identify several responsibilities of a virtual machine: communication and sensor reading, actuator control. This is two instances of the virtual machine that are shown in the figure 7.3. Let us see the figure 7.2 and 7.3. Here 7.2 explains how to instantiate the model. First we will start with the virtual machine, logical machine, and we will set a scheduler for this, and it exhibits, that is, performance critical computation simultaneously. This virtual machine and these two models represents the non-performance critical computation and user interface. Okay, I will stop this video because the recording time is come to an end, and we will continue in the next video the remaining part of this section. Thank you.